everyone. In the last lecture, we have been discussing about different rheological tests. We looked at the constant shear test, the constant shear rate test, and while the first one was for solid samples, the second one was for liquid samples. And then finally, we talked briefly about oscillatory tests that can give you a viscoelastic behavior by looking into both liquid and solid like behavior in one go, because in that test both the shear and the shear rate varies with time. So, today I will take it further and then try to elaborate on how can we separate the liquid and solid contributions in a rheological test. So, basically what we have discussed in the small angle oscillatory shear or the small amplitude oscillatory shear is that we will have the shear varying with time by an oscillatory function. In fact, that is a general oscillatory shear. If it is like a smaller magnitudes, then actually the linear viscoelasticity holds. That is why I add the word small amplitude. Then in that case the gamma dot will be minus gamma dot omega sin omega t, and both of them are out of phase by 90 degrees. So, therefore, we can look at both the change with gamma and gamma dot as two phases of the wave. So, in this case, if I use the formula that we have got from the superposition principle, that is for the case of a linear viscoelastic material, what we do get is the following. So, this was the formula that we have derived in the last lectures, and this is going to be in the case of oscillatory shear as sin of omega t. So, now I will do a change in variables. So, I will define t minus t prime as my t double prime, that would give me minus of dt prime as dt double prime, and what I will get is sigma of t is minus of gamma naught omega, and the limits, the lower limits is for t prime, that is minus infinity. So, for t double prime it is going to be essentially 0, and then I am sorry, it is going to be infinity, and the top limit will going to be 0, and then we will have a dt double prime here with a minus sign, and then we have g t double prime here, and then we have sin omega, I am sorry, it was t prime here. So, it is t minus t of double prime. So, this will become, so I will use one of them, one of the negative signs to change the limits. So, we have gamma naught omega 0 to infinity dt double prime again with a minus sign. And if I do the math, what I have is right now sigma t, if I reproduce the same result here, is minus of gamma naught omega 0 to infinity dt double prime gt double prime going to be sine omega t minus t double prime. So, if I expand the term in the sine, what I will get is sine omega t cos omega t double prime minus sine omega t double prime cos omega t, and this would then give me a gamma naught omega that will be one term, and the next term will be minus gamma naught omega 0 to infinity dt double prime gt double prime cos omega t double prime sine of omega t. So, now what you can notice is this integrands, this entire thing here is a constant because we are integrating for t double prime going from 0 to infinity. Similarly, this is also independent of time because we also integrate from 0 to infinity. Both of them actually are a function of omega. So, essentially I can write this thing as some g double prime g prime omega, and this entire thing I can write as some g double prime omega, where g prime and g double prime are new functions of omega, they are not the derivatives of g. So, with this idea I can write this as gamma naught cos omega t multiplied by g prime of omega minus gamma naught sine omega t multiplied by g double prime of omega. Now, since cos omega t is in phase with the applied shear, that is gamma naught cos omega t, and the sine omega t is in phase with the applied shear rate because that is minus omega times gamma naught sine omega t, what we can think of is this would be something that is of the sort g omega, and this is something of the sort eta gamma dot. So, the first one is g gamma and the second one is eta gamma dot, and therefore, I can think of g prime omega to be a measure of the elastic behavior, and therefore, I will call it a Story's modulus. It characterizes the elastic behavior, and the second term g double prime omega refer to some sort of a liquid behavior because it is in phase with gamma dot. This I will call as a loss modulus, and it characterizes the viscous behavior. So, the first one characterize the solid nature or a solid like nature, and the second one characterize a liquid like nature. So, by doing a single test, I can get both G prime omega and G double prime omega, and of course, the test can be conducted at different frequencies. So, essentially we get a function of frequencies for both storage and loss modulus, and they would then characterize the liquid and solid nature of the sample. So, now we can go a step further and define what is known as a complex modulus using the rules that we use in complex mathematics. And what we do is we recall that exponential of I omega t is equal to cos omega t plus I sin omega t, and using this what we can get is sigma t is gamma dot G prime omega cos omega t minus G double prime omega sin omega t, the result that we had derived just now, and this would then be gamma naught multiplied by the real part of a function g star omega e to the power I omega t, where g star omega is defined as g prime omega plus I g double prime omega. And we can say why this should be the case, because if I do g star omega e I omega t, that is going to be equal to g prime omega plus I g double prime omega multiplied by cos omega t plus I sin omega t. If I look at the real part of this, the first term will come from the multiplication of this and this, and the second term will come from multiplication of this with that, because I multiplied by I is minus 1, and what we do get is g prime omega cos omega t minus g double prime omega sin omega t. That is the result that essentially I am using right here. Okay. So, instead of working with two functions, I can work with one function that is complex in nature, and in that complex function the real part is my storage modulus that characterize the solid nature of it, and the imaginary part is my loss modulus that characterize the liquid nature of it. And as I vary the frequency, essentially what I am doing is I am looking at the response to different amounts of shear or shear rate, because gamma is gamma naught cos omega t, that will change as I change gamma, and also the gamma dot is minus omega multiplied by gamma naught sin omega t, that is also changing with omega. So, essentially we are looking at the behavior for different applied shear or shear rate by simply changing the gamma value. So, essentially the functions g prime and g double prime characterize the behavior of the system that is viscoelastic in nature. Of course, if it is Newtonian liquid, and in fact any other liquid that does not have with no solid nature, what we do get is that the G prime omega will be 0 for all omega values. Similarly, if I have a perfect or Hookean solid, and in fact any solid with no liquid nature, what I will get is G double prime omega is equal to 0 for all gamma. Both of them are indeed the extremes. For the polymer systems, we always get some finite values for G prime omega and G double prime omega that characterize the fact that polymers are both a liquid like material and a solid like material. Depending on the relative magnitudes of that, we can comment on how liquid like or solid like that is. So, let us say if I look at something of this sort, this tell me the solid like nature divided by the liquid like nature. So, if this term is high, it means if it is much higher than 1, we say that the material is mostly a solid. If it is much smaller than 1, then we can say the material is mostly a liquid. If it is comparable to 1, we can say it is viscoelastic, and in there it can be a viscoelastic liquid or viscoelastic solid depending on the magnitude of this quantity. Okay. And this essentially is some sort of the phase of the complex modulus that characterize the relative contributions of these two things. So, now we can look at an example function where we have a relaxation modulus that is given something like this, some sort of an empirical function, and now I want to find the complex modulus for this case. So, G star omega is G prime omega plus G double prime omega, and this by the definitions we have done, G prime omega is omega integral of 0 to infinity dt gt sin omega t, and this has to be, so we can keep a dummy variable here, and this has to be summed with G double prime with an I. So, we have I omega 0 to infinity some dt prime gt prime cos omega t prime. So, this I can write as omega multiplied with 0 to infinity dt prime g t prime sin omega t prime plus I omega cos omega t prime. So, this particular quantity multiplied by omega I can also write as something like I omega e to the power minus I omega t, because that is going to be I omega multiplied with cos omega t minus I sin omega t. We are working with t prime, so it is this, and this will then be equal to I omega cos omega t prime plus, because I multiplied by I is minus 1, plus omega sin omega t prime, which is what exactly we have. We have omega multiplied with sin omega t prime plus cos omega t prime multiplied by I omega. So, we can then write this as I omega 0 to infinity dt prime gt prime e to the power minus I omega t prime. So, now we can use the function that we have defined. Gt is Ge plus g multiplied with exponential of minus t by tau in this particular function, and what we do get is g star omega is I omega 0 to infinity dt prime gt prime exponential of minus I omega t prime, which we can write, if I plug in the gt prime with the expression I had, so if I look at the two terms here, the first term is this, and the second term is something like that. So, I can use, if I integrate this, what you will get is something like Ge exponential of minus I omega t prime by minus I omega, and then if you look at it, this will become a complex number. So, application of limits become difficult here. So, we use a trick here that will be clear once we do it. Instead of doing that, what we do, so we will not do this, what we do is we write the function that we have there as something like this, I omega multiplied with limit s going to 0, 0 to infinity dt prime Ge exponential of minus I omega t prime minus s t prime. So, we add a real term in the power of exponential that will really make our job convenient here. So, what we now get on integration is I omega limit s going to 0 Ze divided by minus I omega minus s exponential of minus I omega minus s or plus s t prime with the limits 0 to infinity. Now you can see that since I have added a small s here, the upper limit now goes to 0 and the lower limit of course goes to 1. So, adding the real number essentially makes our job easier. So, this then gives me I omega limit s going to 0 Ge by s plus I omega, that essentially will give me Ge from here. Okay. We can look at the second term. In second term we already have a real number, so there we do not have any problem. So, that will be I omega multiplied with G divided by I omega plus 1 by tau. So, now if I further simplify it, what I will get is G star omega is I omega multiplied with G E by I omega plus we will have G multiplied with I omega divided by minus omega square minus 1 by tau square, and then we have G by tau divided by omega square plus 1 by tau square, and this will give me essentially G E plus G omega square, the minus signs will cancel, divided by omega square plus 1 by tau square. This becomes the real part, and then we have I omega G by tau divided by omega square plus 1 by tau square. This entire term becomes my G prime omega, and this entire term becomes my G double prime of omega. So, this is how we can really go. This is how we can really go in any kind of an example. If we have the relaxation modulus given, or if it is like an empirical function that we can even try to fit using the experimental results, we can get the forms of G prime omega and G double prime omega for that relaxation modulus, and then if I try to fit using the experimental data, we can see whether the empirical model that we started with is correct or not. So, in this particular case, you can note that in the relaxation modulus, the first term is a constant and the second term decays with time. So, the first term has to be a 0 for a liquid and even for a viscoelastic liquid that eventually at very high times will go to a liquid like state, because then it should not have an elastic modulus. The second term in any case characterize the liquid nature of it, and the first term characterize the more or less the solid nature of it, more or less speaking. In the end, it is ultimately what fits the experimental data best than what should be an appropriate function, because you have a whole diversity of rheological behavior that you can possibly have. So, before we go any further, let me just tell you that in the polymer systems, you do not always have a linear elasticity. You also can have a nonlinear elasticity, that is also very common. So, if for example, my eta, that is the viscosity that we often also call the apparent viscosity in the language of rheology, if this happens to be a complicated function, for example, containing terms like something like these, then these systems will not show a behavior that is linear in nature, and in that case we can still talk about linear viscoelasticity in certain limits of maybe a small shear rates, but the systems overall will not follow the linear viscoelasticity. So, all the kind of math that we did, and actually the starting assumption of superposition that we have used to write the expression for the stress tensor, this is not going to hold for non-linear viscoelastic models. So, the key message is we have to apply some caution. It is not that the storage and loss modulus cannot be found for the case of polymeric systems. Experimental protocols have this machinery built into it, but the expression for the shear stress that is obtained using the superposition principle is not going to be valid. We will have more detailed models to find the stress in terms of the modulus, and that is what I am not discussing in this course. Okay. So, with that I want to conclude this lecture. In the next lecture I will talk about a simple viscoelastic model that is called the Maxwell model, that is used by people working in rheology in analyzing the viscoelastic behavior of systems. What we will notice is that that particular model is not really coming from the molecular principles that we have been doing in this course. This model is rather phenomenological in nature, knowing that the system shows a viscous behavior and an elastic behavior. We can try to build another class of toy model that is completely phenomenological in nature, not starting from the molecular models. So, before we really conclude here, what I also want to mention is that ultimately going from the equilibrium properties and thermodynamics to rheology, we have come really a very long way, and what we haven't really explicitly mentioned is the scales of applicability of those theories. So, when we are doing a rheology, we of course are not looking at a molecular level. At the molecular level, the whole idea of the flow and deformation, the way we have been talking about, doesn't really make as much sense as at the level of larger macroscopic samples. Of course, when we are doing rheological tests, we are doing on samples of sizes of millimeters or centimeters at least, and therefore we have been, over the passage of time in the course, we have been developing more and more larger scale theories that are relatively less accurate, but they cover different kinds of phenomena. So, this is the whole approach, I would say, is sort of a multi-scale modeling approach. We started with molecular models when we were interested in behaviors such as Brownian motion, diffusion, the size of a polymer chain and so on. We started talking about continuum mechanics when we look at the overall flow and deformation of the system. The reason why these two models look very different is not really that there is any new physics that is happening there and is not happening here, but what is more important is that we have no direct way to link the molecular models to, say, rheological or flow and deformation models. So, there are efforts in that direction. So, now we can do, for example, molecular dynamics and try to get viscosities and so on, but those efforts still are limited to very small systems and not yet came in the field of polymers a whole lot. I can do molecular dynamics and get the viscosity of a sample, but those samples will be much smaller than what you can put into a rheometer, and that is the reason why we have been doing rather approximate or phenomenological models which are relatively less accurate, but explain physics at larger length scales than compared to the molecular models. And in this course you have seen a very nice bridge between all these class of models, because we started from a Rouse model. Using that we obtained the expression for viscosity, even if we knew that it did not capture the effect of entanglements and so on, and we discussed detailed models in that direction, but at least it was some effort in that direction. So, the polymer physics essentially is multi-scale to that extent, because we try to use molecular models in various contexts as much we can, and then finally when we give up we go to the phenomenological models. So, with that I want to conclude here, and in the next lecture we discuss the phenomenological Maxwell model that explains the viscoelasticity of polymer systems. Thank you.